Hello, welcome to the term project presentation for Group 16. We are focusing on training game bots by reinforcement learning. Here is the contents of our presentation. I will cover all the introduction and the background information, and afterwards, Erwin and Oscar will cover the detailed information about the games we train the game bots on, and after that, we got some conclusion. First, introduction. I would like to talk about the project origins firstly. There is big news in 2019 in AI area that OpenAI 5 game bot on Dota 2. It beaten the world champion Dota 2 team OG, and it is the first time that an AI has beaten professional esports team on live stream. It is very impressive for us. We all know reinforcement learning is included, and also reinforcement learning is one topic for our course, so we plan to do such kind of project. And we also know reinforcement learning has been applied to game developing in recent years, many examples such as AlphaGo and other games. And so, therefore, our goal for this project is to train our own game bots to play some famous games. Okay, so next I will introduce the background information about the reinforcement learning and some games. First is about the reinforcement learning. Reinforcement learning is the machine learning training method that based on giving positive reward to desirable actions and the negative reward to undesirable actions. So a well-trained reinforcement learning agent is supposed to perceive and interpret its environment and take some optimal actions. So some application areas of the reinforcement learning can be divided into the games. It is definitely our focus for our project, and also other like resource management and the robotics. Some common methods that involved in reinforcement learning has been listed here, among which Q learning is very popular, and also deep Q network will be included in our project. Next, I will introduce about the games we choose to focus on in our project. The first game is Snake, and the second is Super Mario Bros. These are two very famous games. I think you can all familiar with these games. So Snake is the easy one. The award in the Snake game is to eat apple, just to increase the score, right? And the punishment for Snake is to, if you die by crashing on walls or itself, it will introduce a punishment. So for the Super Mario Bros, it's also a famous game, but it's more complicated. For this game, the award will be continue the race just to run and win the game, but the punishment will be die by crashing on enemies or falling into the traps or extra. So that will cause the punishment. These two games will be included in our project. After the introduction of the reinforcement learning and the games, we would like to conclude our summary about our project. Here, in our project, we applied the reinforcement learning to game bots, and we want to try the game bots to play two games. First one is Snake game, and second one is Super Mario Bros. For the Snake game, it is an easy game, but we would like to use it to implement the reinforcement theory. So we try to build everything from scratch, and so we will develop the game itself and try to build the neural network and try to do the reinforcement learning, implement the algorithms and from scratch. And also after that, we will train and test. And for the more complicated one, the Mario, the game itself is very complicated, so it's hard for us to create game environment by our own. So we use some existing platform to create the environments for the game, and we use another reinforcement learning platform to try different reinforcement algorithm on this platform, on the environments. So in this game, since it's more complicated, we will try more algorithms to train the game bots. And after that, we will test whether the game bots can perform well. So that's all the summary of our project. Next, I will talk about the reinforcement learning algorithm that will be included in our project. Totally 3 algorithms will be included. The first one, DQN, it will only be included in our Snake game. So we use the neural network to train the game bot for the Snake game. And the DQN, deep Q network, is used the neural network to approximate the Q function, and it is often used when the state space is very huge. And the loss function in DQN is the MSE loss of the temporal difference target, short as TD target, and the Q network. So this is for the Snake game. And next, there are 2 algorithms that have been involved in the Mario game. The first one is the A2C, Advantage Actor Critic. It is an improved version of the Actor Critic algorithm, and it is one of the algorithm for computing an action based on a state, and then another one to produce the advantage values of action. So the advantage values will tell us how good an action is and how good it can be. The second algorithm involved in Mario is the PPO, Proximal Policy Optimization. The main idea is to take the biggest possible step on a policy without stepping so far that we accidentally cause, and it is cause the performance collapse. And it is one unpolicy algorithm, so it can be used for environments with either discrete or continuous action spaces. These are all algorithms that included in our project. Lastly, I will talk about the programming packages we used in our implementation. First is about mainly three programming frameworks are used in our project. The first one is the PY game. We used to create the snake game from scratch. And also OpenAI Gym and Stable Baseline 3 is used in the Mario games to create the environment and they implement the reinforcement learning algorithms. So for Gym, it is an environmental toolkit for comparing different RL algorithms. And we construct the environments for the Mario using the library Gym Super Mario Bros. And also for Stable Baseline 3, it is a set of reliable implementations of reinforcement learning algorithms in PyTorch. So we use this library to implement the two algorithms, PBO and A2C. And also we use some additional tools to evaluate the agents to tune the hyperparameters and record the result videos.
Thank you, Jihong, for giving us a very nice introduction. So right now, I'll discuss our first game application, which is the snake game. So the first game we packed is the snake game. So the reason we packed this game is because first, it's easy. Second, it was very famous, and most people knows how to play it. And then finally, the training result was very satisfying. So that's why we include this one as an illustration on how to build a game interface from using Pygame and also to train it using reinforcement learning. So basic introductions to the snake game. So the user needs to control the snake, which is represented by the black line in this figure. And the red dot is a snake head, which indicates the direction of the snake is moving. So the user controls the snakes to eat food, which is represented by the green dot. So every time you eat the food, then you will obtain some points. But at the same time, the users need to avoid touching the boundary, which is represented by the brown line, and also to avoid touching the black line, which is the snake body. So otherwise, the game will be over. So let's discuss the framework that we adopt to train this snake game. So we adopt a deep queue network. So basically, we use a neural network to approximate the true queue functions, and then we use another thing called temporal difference target. So we also indicate the loss functions. We use a mean square error loss functions. Our goal is to choose the parameters in the neural network. So it is to minimize the mean square error loss between the temporal difference target and also the queue functions represented by the neural network. So we also need to assign a reward to each motions of the snake. So we assign plus 50 to the snake to encourage it to eat the food. We also assign negative 20 whenever the snake hit the walls or the snake body to discourage it to move towards the wall or towards the snake body. So we assign relatively higher rewards to eating the food because we want to encourage the snake to eat food. But our results is robust if we reduce the amount of rewards to eating the food. So in order to train the game bot to play the game using reinforcement learning, we need to give a state of the game. We need to tells the computer what is the state of the snake game right now so that it can make decisions. So theoretically, we can use an image, we capture almost all the information the snake game it contains. But we found that we can use a much easier ways to reduce the number of dimensions. So the way that we did is to use a finite dimensional state vectors to represent the snake games and to include some important informations that the computer needs to know before making a good decisions. So the three informations that the computer needs to know are the danger nearby, so which is represent whether there's a wall nearby the snake head. The second information is the snake directions, so which indicates that where the snake is moving, left, right, down, or up. And the last information is the foot positions relative to the snake head, whether it is on the left or right, or relative to the snake head. So this slide shows a more detailed descriptions of the three informations that needed to train the game bot. So the danger nearby can be captured by 4 different dimensions of information. So the wall is within 2 steps in the left, right, up, down direction. So the direction of the snake and foot locations are also straightforward. So left, right, up, down. Okay, so altogether we have 12 dimensions in the state vector. So this graph shows the training process. So originally, the game bot moves in random directions, so which means that it can only achieve 0 points for most of the time. But after around only 100 times of training, the games can already obtain 20 points for most of the time. So which is very good because for myself, I play many times, but seldomly I can achieve 20 points. So which means that the computer can already achieve some superhuman performance. So let's see the results here. So on the left, you can see that the snake is moving randomly before the training. So what happened after training? So on the right panel, so let's take a look of our training results here. So you can see that snake is not very smart. So it goes to eat the fruit, and then you see it plays very well, and it doesn't touch the wall as well. So another exercise I did was to try to modify the basic settings. So here we try to adopt alternative structures to train the model. So the second row here one layer 256 neurons was our baseline model, which I used to train the snake game. So I tried to use other different settings. For example, I reduced the number of neurons to 128. I doubled the number of neurons. I also increased the number of layers to 2. So I found that the results doesn't change too much. But only thing here is that when I increase the number of neurons or number of layers, the number of training games required to make the games to obtain stable results doubled to 400. And if I reduce the number of neurons to 128, then the performance is much worse. So I think the model results here is quite robust to model setting. Yeah, so just some add-on here to the snake results. I think it's quite beneficial to extend our model. Instead of using finite dimensional state factors to describe the snake, we can try to use image and train a CNN model to play the game. So we also did this thing, we tried this thing, but we did not include this into the main discussions because the results was not very satisfying. So first, the training time is much longer. And secondly, so after many times of training, the scores obtained by the Game Boy is still very low. So I think it's beneficial to if we can successfully did this thing. So because we also use Pygame to develop another game, a very famous game called Tetris, so which is usually trained using CNN, but given that the snake game using CNN is already not very satisfying, so we did not pursue that kind of directions on Tetris.
The second game we trained is Super Mario Bros. Since the snake game is a relatively easy environment, it is very easy to train a game bot that could master the snake game. As a result, we would like to train a game bot for a much more complex and challenging environment, Super Mario Bros. Since Super Mario Bros. Is a relatively complicated environment, we utilized some programming frameworks to train the game bots, including OpenAI Dream and Stable Baseline 3. We also use Dream Super Mario Bros., a library that allows us to use Python codes to control and play the game, so that we do not need to make the Mario game ourselves. In our project, we trained the game bots using two different reinforcement learning algorithms, PPO, Proximal Policy Optimization, and A2C, Advantage Actor Critic. We also trained our models in two different environments, Super Mario Bros. 1, which is easier, and Super Mario Bros. 2, which is harder. We capture the screenshots of the game as the inputs to the model. The reward function is to encourage Mario to move to the right as fast as he could, and meanwhile avoid dying. Therefore, the reward function consists of three parts. 1. A positive reward when Mario moves right and a negative reward when he moves left. 2. A negative reward for each time frame passes to encourage Mario to move as fast as possible. 3. A negative reward when Mario is dead to discourage Mario to avoid dying, for example, avoid falling in the trap or falling in some hole or touch the monsters. So let's talk about some of the techniques we use to train the Super Mario Bros. AI. The first technique is the grayscale frames. So the screenshots, the frames are turned from RGB, the colorful images, to grayscale images to reduce their image size. That is from RGB, 3 channels, to one single channel. And the second technique is that we reduce the resolution of the screenshots before we give it to the model. So we cut the resolution by each size by half, so that is around 4 times in terms of size. So on the left, you can see an image before this grayscale and reduced resolution processing, and on the right you can see after the processing, the image, the screenshots is grayscale and also a lot blurrier. These two methods can reduce the size of inputs by around 12 times. So as a result, they can reduce the time we use to train the models significantly. However, we use these two methods due to the restriction of our computation resources and time. But it might potentially harm the model's performance in minor ways. The next technique we used is called frame skipping. So in our project, 6 frames are skipped per timestamp to reduce the number of frames sent to the model. This could be done since frames are almost looking the same in a very, very short period of time. So the model does not actually need so many frames in a short time to observe the current state and decide what actions to take. Next, the last technique we use is called frame stacking. So in our project, we stack the last 6 frames of each timestamps. So the frames are not just seen by the models and then get forgotten at once. Instead, they are saved and act as the memory of the model, so that the model can take actions by not only considering the current state, the current screenshots, but also the model can look at and use previous frames to make decisions. So let's talk about the results of our Super Mario Bros. AI. So as what we mentioned, we trained our models in two games, Super Mario Bros. 1 and Super Mario Bros. 2. So Super Mario Bros. 1 is a kind of an easier game compared to 2. So before training, we get a average score of 1372 if we just let the model to decide its action randomly without training. And after training, we get an average score of 2162. So we can see that there's a large heap of improvement of how our Mario is doing in the game. It also happens in Super Mario Bros. Which before training we got an average score of 1254, and after training we get our best model, which scored at 2011. So let's take a look at the results of how is the performance of our game bot we trained. So this is for Super Mario Bros. 1. We actually used two different algorithms, PPO and A2C, to train the models, but the performance is actually almost the same. So we just show one of the results here. So please take a look. So for 1000 steps, you can see Mario is kind of some random actions. It sometimes jump right and sometimes jump left. But because it knows the reward is towards the right, so it often jumps right. So for 10k steps, Mario is doing a little bit better, but still it got stuck for this green pole for quite a long of time. So for 100k steps, you can see Mario start to almost never goes left again, and it is taking a more direct route and being efficient because the reward function encouraged him to do so. And you can also see Mario is going farther and farther. So for 1 million steps, you can see Mario is taking a very, very efficient route, but sometimes it also actually stuck in that green pole for some time. So finally, for 5 million steps, you can see Mario is going faster and faster. It is because it is taking a more and more efficient and effective route. So let's also take a look for the gameplay videos for Super Mario Bros. 2. Again, here we also use two different algorithms, PPO and A2C, to train the models, but the results is actually almost the same. So we just show one of them here. So please take a look. So for 1000 steps, you can see Mario is sometimes jumping left and sometimes jumping right. And you can see Super Mario Bros. 2 is a lot challenging game because there's a lot of monster and traps. So for 100k steps, so here we start to get some result, but again, Mario is often gets stuck in a long green pole. So for 1 million steps, Mario is taking more effective route, and it start to notice where is the monster and try to avoid it. So finally, for 5 million steps, you can see Mario is going faster and faster, and it is very effective, and you can also see it is going very far. So after seeing the gameplay videos of the Super Mario Bros. AI, we can see the game bots are not performing perfectly. In fact, there is a lot of potential room for improvement. So first, we could train the model in higher resolution, so we don't reduce the resolution, so that the input screenshots are in high resolution and less blurry, so that the model can have more information to take action. Second, we can use different stages or even random stages to train the models, and we do not need to start from stage 1 every time like what we are doing now. Third, we can increase the number of time at the frame stack, which is kind of like the memory of the model, maybe from 6 what we are using now to maybe 12, so that the model can use more previous state to decide its actions. So lastly, we can also reduce the frame skipped, so that the model can get the state in time and avoid incoming danger. So less frames are skipped, meaning maybe the model can have kind of like a more time to make reaction and take suitable action to avoid the danger, the monster, and traps. Let's summarize what we have done in our project. So our goal in this project is to apply reinforcement learning on game playing. So we did an easy game, the snake game, and a more complicated game, the Mario game. So for the snake game, we used Pygame to create the game. We used PyTorch to create a new network and use DQN to train the game bot. And we also test it with different settings. So for the Mario game, we used OpenAI Dream and Stable Baseline 3 to set up the environment. We also used two algorithms, PPO and A2C, to train the models for two games, Super Mario Bros. 1 and 2. We also test the performance of the models trained by different algorithms of different games, Mario 1 and 2, and in different number of epochs. And that is the end of our presentation. Thank you.